I say hello, everybody, and welcome to the second of our PDs for your STARS membership, if you like. You're in quite an exclusive club here with your Dobsonian telescopes that have been sent out by Astro 3D. Today, we're going to be talking about filters. Has everybody received their filter packs now? Yes. Yes. Yeah, very nice. Thanks, Tanya. Okay, good. So even if you haven't received them yet, then they'll certainly be on their way, I'm assuming. So I'll just do a share screen. Which one do I want to do? I want to do that one. Has that worked? Very good. Technology is on my side. So I'm going to do the first little bit of this, and then we've got, as it says there, nearly Dr. Jonah Hansen, who's one of the students up here on the mountaintop, who's going to do a more technical spiel at the end. But what we'll do, because the topics are quite disconnected in a sense, just because of the way the material's been done, we'll do questions after mine. We'll stop for questions, and then we'll stop for questions after Jonah's. But if you do want to have any interjections in there, go for it. That's perfectly fine with me. So, go back. So you've probably seen this style of picture before. Very, very pretty, lovely pictures. Here we've got a picture of the jewel box on the left, an open cluster, and we've got 47 Tuck on the right there, which is a globular cluster. And these are absolutely spectacular images, but I'm sure you can appreciate that this isn't what they will look like through your telescopes for multiple reasons. And one of those reasons is that these have actually been digitally enhanced by a digital version of the filters that you've got, or slightly more sophisticated versions of those. But what we're hoping to be able to talk about is the fact that these sorts of colour filters are what you've got and will enhance what you can see through the telescope in the night sky. A filter that you're probably familiar with is these lovely polarizers. I only like polarizers. I don't like the tinted sunglasses. And the main reason for that is that the light that comes at you is coming at you, the light being a wave. The light will come on this angle, it'll come on sideways angles, it'll come on all different ones. And the light that comes from the sun is a completely homogeneous mix of all of that. They're coming on equal proportions of all of those different planes, if you like. But as you can see in this image here, if you were to go out on the water, or you're out on the road and you've got the concrete in the asphalt, as the light hits those surfaces, it will come back on a horizontal plane. And that's what causes all of that awful glare. And the polarizing sunglasses will absorb the horizontal bits or the horizontal components of that light and then reduce the light by about 50% then, which then helps you to be able to pull out all the details of what it is that you're seeing, what you're looking at. And some polarizing light is something that Jonah might talk about a little bit later as well in a bit more detail. The filters that you've got, though, are the coloured ones. And so that diagram pretty much sums it up. If you have all the colours of the rainbow and you have a green filter, then only the green light will be allowed through. And if the science that you're looking at is quite specific to only certain colours, then these filters are hugely useful because it can throw away the light that you're not interested and just focus on the bit that you are interested in. Filters in particular are good at throwing away a lot of the light, or bad, depending on which way you look at it. Mirrors tend to throw away about 1% of the light that hits them. Filters can throw away up to 80% or more. And that's something to consider when you're using your telescope. So your filters should be those four. So you've got a dark yellow, an orange, a green, and a dark blue. And just out of interest sake, if you wanted to read up a bit more on where those numbers come from, they were from the Rattan numbers, somebody of the surname Rattan, and they're also related to the Kodak colours from the photography company. But what I'll do is just show you what to do. So I have the eyepiece, You should have all got the eyepiece on. I've still got the caps on them, so I'll just take these caps off. So that's the bit you put your eye to. And then you take the suction one off the back, and you'll see there's the screw in there. You've got your filter. Really simple. Open the pack, take out, got the yellow one here, being very careful to only touch the edges. This goes in that end, it just screws in nicely. And there, of course, I'm not going to do it on camera, is it? And then, as per normal, you would just screw that into the telescope, into its normal position. And in theory, you could put multiples on if you so wish to mix and match. And the one that you might think about putting it to be mixing with this one would be the neutral density filter, which just blocks a large proportion of the light, all at an equal level for all of the optical wavelengths. All of the colors will be dropped down by the same amount. And then that could also go on there. I realized as I was looking through the untouched one, untouched one on my desk earlier, it had a giant fingerprint in the middle. And we know that this sort of thing happens. Much as you can be careful, you can still get them dirty. So I asked an expert this afternoon who is well renowned for his expertise in filters, and he says that particularly these ones that you've got, you can just treat them the way you might your spectacles. So the same way that you would clean your spectacles, you can clean these. But of course, the ideal is to not get them dirty in the first place if that can be at all avoided. Right. One. Okay. So the first filter, just go through them one by one. So the dark yellow one. So this one will allow about 83% of the light through, and that's actually quite a bit. So it's quite useful looking at the moon when it's half to full and details on the surface like the Maria, so the big rivers of basalt, the mountains, the craters, the ridges will all be made quite clear. If it's still too bright, as we said earlier, think about using the neutral density in combination with the yellow, but remembering that as soon as you add more filters, you are cutting out more and more light, and that works out as a proportion combined. I'll also just spruik our resource on our website, which is a student workbook and teacher notes on how to observe the moon, and some follow-up questions and support recommended websites in there, just because we put some effort into that. Hopefully that should be useful for you as well. The number 12 is also useful for looking at the darker belts in Jupiter. And similarly with Saturn's atmosphere, though not quite as boldly as with Jupiter. The number 21 orange filter, I don't have with me. But this one will cut out, as you can see in that thing at the top there, will cut out the violet, the blue, and some of the green. These aren't as precision-built filters as the ones that Joan is going to talk about later, and so there is a bit of bleed into the green there. But to all intents and purposes, it's really the red and orange and yellow bit that's most strongly in there. So because this one then blocks out about 50% of the light, you'll need a clear, bright night and good visibility of the objects that you're looking at. And so you want the same sorts of conditions for observing that a professional astronomer might use. So you want low wind, low humidity, no cloud cover, and so on. And of course, the less atmosphere you're looking through, the better as well. From a general standpoint, the twilight sky will also be darkened and will make things stand out in the sky more. So if you're going to be choosing what things to look at, Venus is a good one to look at with this one. So Venus has a thick atmosphere, and the orange filter will allow us to look deeper into the atmosphere, and you might end up seeing different cloud shapes with that filter than you would if you were just using the white light on its own. You can also look at Mars, and Mars, of course, is famous for its dust storms, and some of them can last for months. The orange filter can help you to see it can increase the contrast between the light and dark bits and help to penetrate the clouds as well. And you can use this one for the moon. So it'll make the seas of basalt darker and emphasize small detail along the terminator, along the shadow line. And as before with the orange, it'll help with the banding of Jupiter to be seen more clearly and highlight the bluish swirls within those bands. I just want to point out that this is taken from a web page. Although those pictures look really fuzzy, our eyes will be able to integrate more nicely than that. So one thing to try and remember is to be patient when you're using them and to allow your eye to settle in to what's being seen. And after a while, your eye will attune and you'll be able to see a lot more detail. So something to be encouraging the students with as well is to not be too rushed, to take their time to get this thing in focus and get their eye adjusted to what light is coming through. The light green. So there are a number of green filters that are possible to use through the Ratten series, but the one that we've sent you is the 56 light green. This will help to accentuate the surface features on Jupiter. And one of the tips for this one is look at Jupiter without the filter. And if you can see the great red spot nice and clearly, then add the filter, and that'll make the spot even more prominent than it was before. It's also good to look for looking at the moon's surface, and for looking at Mars, it'll make the polar caps stand out more. And the 80A is the medium blue. And if you were to Google this one, this is the most popular one that gets referenced by amateur astronomers. It allows less light through than any of the other filters that we've talked about, but it is still quite useful. Keeping that in mind, you need to then think about looking at bright objects. Again, good looking at the great red spot, as particularly if the spot is in the middle of the face of that Jupiter is pointing at us. It can make the red-brown bands on Jupiter look darker so that they stand out from the white. And if there are any storms, then those storms will also stand out better with this filter. If you want to look at the moon, look away from the terminator and it'll bring out the craters and the Maria. And for Mars, it'll bring out the clouds, the hazes, and the poles. Are there any questions? No? Well, in that case, I will introduce Jonah.
Hello. Some familiar faces here. That's cool to see. See you guys. Yes. So my name's Jonah. I'm a soon-to-be ex-PhD student. Submitted my thesis a couple months ago and just waiting to get it all back. But I'm going to be talking to you kind of less about the amateur astronomy side of things, using how to use filters, and more how do professional astronomers use filters. And so I'm just going to share my screen. Hopefully you can all see that now. In particular, the main use of filters is something called photometry. Now, you've probably seen lovely pictures of galaxies and things from telescopes like the Hubble Space Telescope. But the thing is that most astronomy telescopes don't actually take colored images. They take grayscale images. And so in order to get the colors, what we do is we use the filters. So for instance, we've got this lovely picture of a galaxy here. And what we might do is we might take, say, 7 different images using different filters. So we'd use an ultraviolet, kind of a very deep purple filter, blue, green, etc. And then by taking these images and stacking them together, we can get these lovely colored images that you're probably more familiar with. And it's of advantage to us because grayscale detectors that just simply measure the intensity of light that hit them, not caring about color, are generally more sensitive and give us more properties than a color detector would. And so it makes sense to instead use filters and kind of really fine-tune what we're wanting to look at. Now, the first thing that photometry is good for is particularly, looking at the colors of stars. So what I've got here is basically it's a plot of the intensity of a star and wavelength. And when I talk about wavelength, you can basically think of that as the color of light. And so the colors that we're used to seeing are kind of overlaid here, typically between about 400 nanometers and 650 nanometers or so. Now, the temperature of a star will affect its color. You can kind of see this visually when you look at, say, a match or a Bunsen burner or something like that, where a lower temperature flame, like a match, it's typically a reddish orangey color. And when it's made a lot hotter, or if you're looking at the very center of a flame, it burns blue. And that's because it's hotter. And it comes from a law called black body radiation. And you can kind of see this here in this plot where different temperatures of stars have different curves here. And they kind of peak at different colors. So if you've got, say, a star with a temperature of 4,000 Kelvin, it will appear kind of reddish. If you've got a star up at 6,000 Kelvin, it will appear bluish. The sun is about 5,700, so it actually kind of peaks in the green, but to us it appears kind of a yellowish, whitish color. And so the reason that this is useful is that if we measure the color of a star using different filters with different colors, we can kind of start to work out where on this plot our star might be and kind of infer what its temperature is. So you might have seen a plot like this if you're doing astronomy curriculum. This is something called an HR diagram, where more or less stars of all sorts, of all different types, masses, ages, you can plot them on one lovely diagram. On the x-axis, you've got the temperature of the star. On the y-axis, you've got the brightness or luminosity. And so different stars will lie on different parts of this plot. So here in the middle, we've got what's called the main sequence. This is where stars spend most of their life. Our sun is kind of right there in the middle. It's going to stay there for another couple of billion years. But eventually, as stars age, they start to move around this plot a bit. In particular, our sun, when it starts to age, it'll move up to the top right. It'll increase in size and it will get a lot cooler. And then eventually it'll kind of cool, it'll kind of heat right up again, but become a lot dimmer and become a white dwarf. And so this plot contains a lot of information about how stars age over the course of their life. But you might wonder, so intensity, that's very easy to measure. You just measure how many photons are hitting your detector. But how do we determine this temperature? Well, again, we use filters. This is the exact same plot, except using a revolutionary space telescope called Gaia, which basically is producing the most accurate map of the Milky Way that we know of. And if you notice on the bottom, the x-axis there, it doesn't say temperature. Instead, it says this weird thing, GBP minus GRP. And all that's saying is it's taking the amount of light through a blue filter minus the amount of light through a red filter. The difference in colors is directly related to the temperature of the star. And that's why in the top, you can actually see that it's directly related to temperature. And so by taking the difference between two filters, we get the temperature. And then if we know the intensity, we can work out where a star lies on this lovely diagram. Now, I'm going to walk through some other things that we can tell about stars, and in particular, kind of be basing it off of this particular telescope. So this is the SkyMapper telescope. It was originally a project for one of the telescopes we've got up at Mount Stromlo, where its purpose was basically to map the entire southern sky every couple of nights. And this is something that's been done in the northern hemisphere for decades now, and we thought it was time to do it in the southern hemisphere. And this is very useful, not just for getting a good survey of the night sky, but if there's, say, a supernova or something changes, because it's happening so regularly, we're able to really pick up on supernovae and other sources. Unfortunately, it was running for less than 2 weeks before the 2003 Canberra bushfires happened. And so, unfortunately, SkyMapper didn't last long for this world. But we thought it was still a good idea. So we built a new dedicated telescope for it up at Siding Spring Observatory north of Dubbo, where it's still running quite well today. And because we're able to build a brand new telescope, we were able to design the filters from the ground up for this task. And so here you can see SkyMapper has 6 filters. They're labeled U, V, G, R, I, and Z. You might be able to kind of guess what some of them might stand for, U being ultraviolet, R being red, G being green. Some of them are more to do with being in the infrared, which is where the I comes from, and Z is a deeper infrared band. But these have been designed very carefully in order to extract very specific properties from stars that it looks at. Now, these filters are very much treated in a very carefully made so that we can get as much light through them as possible. So whereas some of your filters might not allow a lot of light through, they might decrease the amount of light. We want to try and avoid that effect, because the more light is blocked by our filter, the longer we have to stare at the star, and operating a telescope takes a long time and it costs a lot of money. So we want to kind of reduce those effects. And so to do that, what we do is we coat these in special coatings, kind of like polarized sunglasses or tinted sunglasses. But the purpose here is really to enhance the transmission. So regularly on, say, sunglasses or regular pieces of glass, you might have about 4% of the light reflected rather than going through the filter. Whereas if you've got this lovely anti-reflection coating, it's called, you can reduce that to 0.1%. And so you can kind of really see the difference in that image there. And of course, you can have multiple coatings. So maybe you want a polarized lens, and then also a anti-reflection coating, and all sorts to make it as best as you can. Now, the first kind of detail that we can start pulling out using filters is something called surface gravity. It's basically measuring what's the gravity or the acceleration due to gravity on the surface of the star or the planet or the whatever you are looking at. So for Earth, we've got the traditional 9.8 meters per second squared. That's the acceleration that's pulling us down on the surface here. And typically in astronomy, we take the log of that number in a system of units called CGS, which I find very strange, since CGS stands for centimeters, grams, seconds. So in astronomy, where we're dealing with some of the largest distances and heaviest things we know, we're measuring things in centimeters and grams rather than meters and kilograms, which it's due to history, but regardless, it's the standard that's been set. So Earth, for example, if you take the log of 900 centimeters per second, that's about 3. A white dwarf has a log G of about 8. And a neutron star, some of the densest, heaviest things that we know of, has a log G of 14, which, to put that in perspective, 1 teaspoon weighs about the same as 500 pyramids, which I find is a kind of a fun fact. So these are incredibly dense, huge amounts of gravity on these objects. And we can work out what the surface gravity is simply by using filters. So on this plot, what I've got is, this is from the SkyMapper filters. So if you take the green filter minus one of the infrared ones and plot that against this combination of different filters, what you can see is that stars of a higher surface gravity tend to be higher up on this plot, and stars that are lower surface gravity are lower. And so if you can measure where your star is on this plot, you can work out roughly what its surface gravity is. You can also kind of tell different types of stars apart. So up here, we've got some main sequence stars in blue, and we've got another type of kind of a hotter star called a blue horizontal branch star, kind of sitting down lower. And so these types of diagnostic plots can tell us a lot about what a star is doing. Now, there's another thing that we can do, and this is kind of getting into, I suppose, chemistry of stars. Now, you may have seen this, and I hope you have. It's a wonderful, this is the astronomer's periodic table, so to say. And there's a resource, and you can grab this online from the Astro 3D website, and order posters for your own classroom if you'd like. What these are, this is basically the periodic table, but what it's telling us is where these elements come from. Whether they come from the Big Bang, maybe they come from merging white dwarfs or neutron stars, and it tells us the relative abundance over time. So it's a lovely periodic table. Unfortunately, this is not the one that astronomers tend to use. The real astronomer's periodic table looks like this, where we've got hydrogen and helium, and everything else is a metal. You might argue with me that oxygen or nitrogen are not metals, but I disagree. It's mostly to do with the fact that hydrogen and helium were produced in the Big Bang, and everything else, minus a tiny bit of lithium, were produced in stars merging. And so it kind of gives us a useful diagnostic for when stars were formed. So this comes to the term metallicity. which is basically the chemistry of a star, or how much of the star is made up of elements other than hydrogen or helium. And we measure this basically in terms of iron. Iron is the one that's used the most often because it's the hardest to break down. A star, when it's burning up through its fuel, once it hits iron, it's no longer able to burn and it will explode in a supernova. So it's kind of like the end of the line. And it's also very easy to measure in terms of, it's easy to measure the iron abundance of a star. So what we do is to calculate this is we basically measure how much iron is in the star with respect to the amount of hydrogen we can measure, and then take the logarithm and compare that to the sun. So if you've got an Fe/H of 0, that means that you've got the same amount of iron as the sun has, or the same amount of metals as the sun has. If you've got a positive number, it means you've got more metals. If you've got a negative number, it means you've got less. And this is very important in the field of galactic archaeology. You can kind of think of this as like donning Indiana Jones's hat and trying to uncover the history of our galaxy. And in particular, what we want to do is we want to find the oldest stars, the very first stars, the stars that were first formed after the Big Bang. Because the stars that were formed after the Big Bang, they don't have any metals in them. They were formed from just this primordial hydrogen and helium. And so we shouldn't measure very many metals at all. And so if we can measure the metallicity and we find that it's very, very low, we're talking a very large negative number, that gives us a good hint that these are some of the older stars in the universe that we're looking at. And once again, filters is a good way to measure or approximate metallicity. So here's a plot that I've actually used in my own research where I've got some different filters. Here I've got a green filter minus a deep infrared filter, and then this is an ultraviolet minus a blue filter. And in color, what we've got is the different metals of the star. So kind of pinkish is the same as the sun. And it kind of varies basically between 1 and -1. Metallicity doesn't change an awful lot. And you can see that these stars kind of lie on a spectrum. So if you can kind of measure where a star falls on this plot using your filters, you can then kind of estimate what the metallicity is. And again, here's a similar type of plot, except using the SkyMapper filters, where you can see that these different lines are separated quite drastically. And in particular, this filter here, the V filter, this kind of violet filter, was specifically designed in mind to try and estimate the metallicity of very distant stars to try and find some of these very first ones. And one of the most metal poor stars that we know of is this -5.4. So we're talking 10,000, 100,000 times less than the sun. This is a very primordial star. And it's very high up on this plot. If you've got a star that's further down, it's less interesting to us. How am I going for time? Let's just have a quick look. Oh, yeah. So another thing, kind of taking a bit of a different track, is polarization. Lara mentioned it at the very beginning. You've got your polarized sunglasses. And what you can actually do is you can actually see how they work by looking at a screen. Because a screen's light is typically very polarized. That means that the electric field of your light wave is tilted mainly in one direction, whereas sunlight is pretty much in any direction. And what you can do is if you take your polarized sunglasses and you kind of rotate around, eventually you'll find a point where the sunglasses are blocking all the light from your screen. And that's the point where all of the polarized light from your screen is basically being absorbed by the filter and leaving no light to go through. If you then rotated around 90 degrees again, suddenly it will look like as if you hadn't had sunglasses at all. It would look like if it's just a clear piece of glass. And what we can do is we can use the same thing to look at the universe. And in particular, a well-known phenomenon is the fact that when light bounces or reflects off of dust or other things like that, it gets very polarized. So what I'm showing you here is this is a map of the Milky Way. You can kind of see that band in the middle there. And this is showing you the polarization signal. So what we've done is we've taken a polarized filter, we've taken an image, then we've rotated that filter 90 degrees to let the other polarization through, and we've taken the difference between them. And so when it's blue, that's saying that the light is basically not polarized, that there's no difference when you've got horizontal polarization or vertical polarization. Whereas in the middle there, where it's kind of deep red, that's saying that it's very polarized. And this is tracing out the dust in our Milky Way. And you can see that disk of the Milky Way is very dusty. And we can actually just see that with our eyes. You can look up, and if you've got a very nice dark night, you can see the Great Emu in Aboriginal astronomy, which is made up of all these dust clouds of the Milky Way. But using polarization gives us a very easy way to kind of probe the dust. And that's just simply using a filter and rotating it 90 degrees. You can do the same thing at even smaller scales by looking at the dust around stars. Again, when light is reflected off of dust, it's typically polarized, whereas if light is just coming straight towards us, it's unpolarized. And so on the right here, what I've got is basically a plot of when you see a wavy signal, that's saying that it's very polarized light. Whereas if it's just flat at one, it's unpolarized. And the different colors are kind of us probing different resolutions. So some of the purplish colors are looking straight at the star, and then you're kind of looking further and further away from the star until in that top plot, you can see we hit this dusty disk. We get this lovely sinusoid picture of where the dust is. And in comparison, on the bottom plot, this is a different star. There's no dust there because it's all pretty much at one. So we can use these techniques to kind of probe the dust around other stars as well. And finally, the final thing I'll talk about is narrowband filters. I believe that you may also, if you haven't received one, you may eventually receive a solar filter for your telescopes. And these are a type of narrowband filter. In particular, I believe they're actually this exact filter that I'm showing here. So when in astronomy, we don't just look with these broadband filters. We also like narrowband filters where you're more or less probing a single spectral line. So, when you've got an atom in a star or a galaxy or in a gas cloud, it'll absorb a very specific color of light. It's kind of like a thumbprint. So, for example, with hydrogen, about 656 nanometers, it will absorb a very, very specific shade of red. And you can kind of see this here. In this star, there's a very strong, or here it's an emission line, so it's actually emitting a lot of light at this very specific color. And so you might want to be able to measure how much hydrogen is in your object or your gas cloud by just looking at this one line. You're not letting any other types of elements come in. And so for that, you get a very narrow, you let only a very tiny sliver of light through. And here, this is an H-alpha filter, what it's called, or at about 660 nanometers. And it lets a very thin sliver of light through to measure how much hydrogen's in a star. And this is exactly what's used when you're doing solar observing, because you only want a tiny amount of light coming through. In fact, a narrowband filter is not enough. You also need an extremely strong neutral density filter to filter out about a million times the light that would otherwise come through. Now, typically, when we're doing this type of thing, we don't tend to use narrowband filters an awful lot unless it's a very specific case, like looking at the sun. Instead, we'd use what's called a spectrograph, where we split the light into all the colors and measure all the lines at once. But that's a story for another time. And I think in a month's time, the astronomer who will be talking to you about globular clusters will probably talk a little bit about spectra then. So yeah, also happy to take any questions you might have.
Run silence.
I thought that was brilliant.
Oh, thank you.
Yeah, no worries. I've done a little bit of mucking around with this myself and stuff in the past, but it was a really good explanation of how we can use them. Just thinking about when we're using these telescopes with students, I mean, it's a lot of mucking around to take an eyepiece out and switch the filters in the dark and not lose the filters, etc. So is that something you'd recommend, or are we heading towards the concept of imaging, simple imaging and stuff like that?
Lara, if you want to take, otherwise I can throw in my 2 cents.
Yeah, I think you try that with Jonah.
All right. So what I would probably do in this regard is what you might want to do is you might want to have the filter off to begin with. Look at whatever you're looking at. Maybe it's the moon, maybe it's Jupiter or Saturn. And then after you've had a look, what you might want to do is then put the filter on and then let them all have a go again and try and see if they notice any difference, or if anything else kind of pops out. And that's kind of a way that you can kind of also show, like, filters are blocking out certain parts of light, and so you're able to see the different contrasts a bit clearer. And that way you're only switching it maybe once instead of doing it at each student, because that would be quite tired, quite problematic.
Yeah, that's right. Yeah, brilliant. All right, thank you.
No other questions? No. Well, hopefully with all this clear weather that we're having lately, we'll all be able to go out there and have a go. And we'd be very interested to hear and see any pictures that you take using them all, and see what your feedback is. And if there are any particular tips and tricks that you come across when you are using them, then we'd be more than happy to share that amongst all of the other STAR teachers. Thanks, Tim.
No, I was just going to say, Lara, last night I ended up doing a sort of STAR party with the school, and it was pretty random. We had some of the local telescope club come in as well, and we were helping them out. And we had our 2 there. 2 was enough to manage and keep on track. Little kids think they can lean on telescopes. Oh my God. That was so much fun, trying to realign telescopes and take children off the fallen telescope and everything else. But it was really successful, and the imagery out of those 8-inch dobs is gorgeous. The pictures, we focused mostly on the moon because the sky was not really conducive to much. And I let the astronomy club people do the complicated stuff with their bigger telescopes, but really successful, really great.
Excellent. From that point of view, Jonah, you do outreach up here. Do you have any other tips for that sort of crowd control side of it?
You just gotta be patient.
Patience.
It's inevitable. Lines. They're going to knock it, and so you just got to be prepared to keep moving it back.
Actually, the thing that I found the most useful was the location of the finder scope. If once I'd tuned the finder scope, because this was sort of our first time out at night, I could, once I'd sort of done it a few times, I could just use the finder scope to put it back in place, and it would be right on the money for the students. So that was good to be on the opposite side of the telescope and sort of correct it quickly. But with 2 of them, of course, it was that's right. It was fun.
Good to hear.
Very good. All right. In that case, if there aren't any more pressing questions or comments, we might leave it at that, and we'll see you again I think it's about a month until the next one. So I hope you all enjoy your break or your student-free time, and you come back refreshed. And you're most welcome. And we'll see you next time.